Imagine being handed the most impossible mission ever conceived by human minds. A mission where failure isn't just likely, it's almost mathematically guaranteed. You're told that somewhere out there, beyond the familiar embrace of our solar system, an object likely several kilometers across is racing away from us, at speeds that make our fastest rockets look like they're standing still. It's already past the sun, it's already leaving, and you have an extremely short window, far too little time, to figure out how to stop it. What makes this scenario truly impossible? We're not trying to catch something coming toward us. We're trying to catch something that's already gone. Now, before you click away thinking this is some doomsday scenario you need to worry about, let me be completely transparent with you. We don't actually need to stop 3i Atlas. This interstellar visitor poses absolutely no threat to Earth. It's not going to hit us. It's not coming back. Scientists have calculated its trajectory with extraordinary precision, and we're perfectly safe. So why are we even talking about this? Because the question of whether we could stop it, not whether we should, but whether we physically could, reveals something profound about where humanity stands right now as a spacefaring civilization. It exposes both our capabilities and our limitations in ways that matter far beyond this single comet. Think about it this way. For all of human history, we've looked up at the sky and felt small. We've watched comets streak across our atmosphere, witnessed meteor showers, studied asteroids from a distance, and wondered what we'd do if something actually threatened us. We've made movies about heroic missions to save Earth, where a ragtag team of astronauts launches at the last minute, lands on the asteroid, plants some explosives, and saves humanity with seconds to spare. We've imagined we could handle it if we needed to. But what if we actually tried? What if we took everything humanity has built, every rocket, every nuclear weapon, every ounce of scientific knowledge we've accumulated, and pointed it all at one objective, stopping an interstellar object that's already moving away from us faster than anything we've ever sent into space? This isn't about fear. It's not about preparing for some catastrophic event. 3i Atlas is safe. We're safe. But asking this question forces us to confront something most people never think about. The vast gap between what we imagine we can do and what we can actually accomplish with the laws of physics, the technology we have right now, and the brutal constraints of time and distance that govern everything beyond our atmosphere. When you strip away the Hollywood special effects and the dramatic countdowns, when you sit down with actual orbital mechanics and propulsion physics and momentum calculations, what can we really do? Could we catch something moving that fast? Could we change its course? Could we even reach it before it disappears into the darkness between stars, never to return? Here's what makes this question so fascinating. 3i Atlas isn't some hypothetical object. It's real. It's out there right now, moving through our solar system on its way back to interstellar space. We've observed it. We've photographed it. We know its size is uncertain but estimated between a few hundred meters up to around 5 or 6 kilometers across. We know its speed, moving far faster than anything gravitationally bound to our sun. We know its trajectory, a hyperbolic path that brought it past our star and is now carrying it away forever. And we know that if we wanted to do something about it, we'd have only the briefest window of opportunity, a window that's already closing even as we speak. Time matters critically. Every week matters. Every moment it travels, it gets farther away, harder to reach, more impossible to intercept. So what would it take? If some cosmic authority suddenly told us we had to stop this thing, what would our options be? Where would we even start? Would we use nuclear weapons, the most powerful tools we've ever created? Would we try to ram it with a spacecraft at high speed, like we did with NASA's DART mission that successfully altered an asteroid's orbit? Would we attempt something more elegant, like positioning a spacecraft near it and using gravitational attraction to slowly pull it off course? Or would we discover, after running through every possible scenario, that we're simply not ready yet, that despite all our technological advancement, despite landing rovers on Mars and sending probes beyond Pluto, despite our satellites and space stations and planetary defense systems, we still can't catch something that's already leaving? Stay with me for the next 20 minutes or so, because we're going to walk through this together. We're going to examine every realistic option humanity has for stopping an interstellar object. We're going to look at the nuclear option, the kinetic impactor approach, the gravity tractor concept, and everything in between. We're going to run the numbers, face the physics, and see what's actually possible versus what's pure fantasy. And along the way, we're going to learn something crucial about where we are as a species that's just beginning to reach beyond our home planet. Because understanding what we can't do yet is just as important as celebrating what we can already accomplish. This investigation isn't about giving up or accepting defeat. It's about honest assessment. It's about looking at 3i Atlas racing away from us and asking the hardest question. With everything we have right now, with all our rockets and all our knowledge and all our determination, could we actually pull this off? Could we launch something fast enough to catch it? Could we deliver enough energy to change its trajectory? Could we coordinate the mission, build the spacecraft, calculate the intercept, and execute the plan in the extremely limited time available before the window closes forever? Or would we watch, helpless but informed, as it slips beyond our reach? Here's what I want you to understand before we dive deeper. This isn't a failure of human capability. This is a lesson in reality. Space is unimaginably vast. Speeds at interstellar scales are incomprehensibly fast. The amount of energy needed to alter the course of something several kilometers wide, moving at those velocities, is staggering, and time, once lost, can never be recovered. These aren't limitations we've chosen. They're constraints imposed by the universe itself, by the laws of physics that govern everything from the smallest particle to the largest galaxy. Working within those constraints, with the technology we've developed so far, what can we actually achieve? Before we answer that question, I want you to do something. Drop a comment right now telling me your first instinct. What would you try if you had to stop? 3i Atlas, nuclear bomb, giant rocket, some kind of laser, a gravitational trick? Be honest. Don't overthink it. Just tell me what your gut says would work. Because I'm willing to bet that as we go through this analysis together, you're going to discover, like I did, that the obvious answers aren't nearly as simple as they seem. Let's find out together whether humanity could actually pull off the impossible mission, or whether 3i Atlas represents a challenge we're not quite ready for yet. The answer might surprise you. Let me paint you a picture of how this scenario plays out in movies. The scientists detect a threatening object. They call an emergency meeting. The president authorizes immediate action. Engineers dust off plans for a special spacecraft that's been in development. Within days, maybe weeks, a crew launches into space, intercepts the object, plants some kind of explosive or thruster package, and successfully alters its course. Earth is saved. Credits roll. Everyone goes home feeling like humanity can handle anything the cosmos throws at us. Now let me tell you what reality actually looks like. Because the gap between those two versions is so enormous, it might as well be the distance between Earth and 3i Atlas itself. Every single assumption that makes movie scenarios work falls apart when you apply real physics, real engineering constraints, and real timelines. Let's start with the most fundamental problem. 3. Atlas isn't coming toward us. It already passed the closest point it will ever be to both the Sun and Earth. Right now, at this very moment, it's racing away from us, heading back toward the vast emptiness between stars. That changes everything. When something is coming toward you, interception is challenging but theoretically possible. You can position yourself in its path. You can time your approach to meet it at a calculated point. You have the luxury of the object doing half the work, covering distance toward you, even as you move toward it. But when something is already moving away, when it's already past you and accelerating into the distance, you face an entirely different problem. You have to catch up. You have to not only match its current speed, but exceed it, build up enough velocity advantage to actually close the gap, reach it before it gets too far away, and still have enough control to do something meaningful when you arrive. It's the difference between catching a ball someone throws to you and trying to catch a bullet that's already been fired past your head. Consider the speed we're dealing with. 3i Atlas is moving on what scientists call a hyperbolic trajectory. That's not just technical jargon, it's a specific mathematical description that means this object has enough velocity to escape the Sun's gravitational pull entirely. It's not orbiting, it's not going to loop back around. It came from interstellar space, passed through our solar system, and is returning to interstellar space, all without ever being captured by our star's gravity. The speeds required for that kind of trajectory are staggering. We're talking about velocities far beyond what we typically deal with for bound objects in our solar system. Think about our fastest probes. The Parker Solar Probe reaches incredible speeds by diving close to the Sun and using its gravity to accelerate. Even so, we're talking about speeds that took years of mission planning, multiple gravity assists, and extremely precise orbital mechanics to achieve. 3I Atlas is moving at interstellar escape velocities, and it's moving away from the very gravity wells we'd need to use for acceleration. There's no slingshot maneuver available. There's no gravitational boost waiting to help us. We'd be chasing something that has every advantage while we have none. Now let's talk about distance. By the time we detected 3I Atlas, identified it as an interstellar visitor, calculated its trajectory, and confirmed it was leaving our solar system, it had already put massive distance between itself and Earth. Space operates on scales that human brains aren't built to comprehend easily. When we talk about astronomical units or light minutes, or the distances involved in interstellar travel, we're discussing spans so vast that even travelling at thousands of kilometres per second, it would take months or years to cross them. And every hour we spend planning, building or preparing is an hour during which 3I Atlas travels farther away, making the catch-up problem exponentially worse. Here's another critical difference from the movies: launch windows. When NASA sends a mission to Mars, or when we dispatch a probe to Jupiter, we wait for optimal launch windows, specific periods when the orbital mechanics align to make the journey possible with the fuel we have available. These windows are calculated years in advance. They depend on the positions of planets, the trajectories we can achieve, the gravity assists we can utilize. Miss the window, and you wait for the next one, which might be months or years away. For 3I Atlas, there is no optimal launch window coming up. There's only now, and now is already slipping away. Let me give you a reference point that makes this visceral. Think about NASA's DART mission, the one that successfully crashed a spacecraft into an asteroid and changed its orbit. That mission was an incredible achievement, a genuine milestone in planetary defense. But look at what it required. Years of planning and preparation, detailed study of the target asteroid, carefully calculated trajectories, a target that was already in our solar system on a predictable orbit, an object that was essentially standing still compared to interstellar speeds, and a goal that was simply to nudge it slightly, not to stop it entirely. DART had every advantage: perfect knowledge of the target, years to prepare, a cooperative orbit, a relatively small deflection goal, and it still took extraordinary effort and precision. Now imagine trying to do something similar to 3I Atlas, but with none of those advantages. No years to prepare, just an extremely short window. No convenient orbit, it's leaving on a hyperbolic escape trajectory. No detailed prior study, we barely know what it's made of. No modest deflection goal, you'd need to completely alter its course to stop it. And perhaps most critically, no spacecraft anywhere near ready for the mission. DART was specifically designed, built, tested, and launched for its particular task. There is no 3I Atlas intercept spacecraft sitting in a hangar somewhere waiting for authorization to launch. Such a vehicle doesn't exist. This is where the movie version falls apart entirely. In films, there's always a spacecraft ready or nearly ready, some program that just needs funding approved, some brilliant engineer who designed something perfect for exactly this scenario. In reality, designing and building a spacecraft capable of the speeds and maneuvers we'd need would take years minimum. We'd need to figure out propulsion systems, navigation, communication, power, structure, payload, and hundreds of other engineering challenges. We'd need to test everything. We'd need to build it. We'd need to transport it to a launch site, integrate it with a rocket, prepare for launch, and actually launch it. All while 3I Atlas gets farther away with each passing hour. The fundamental challenge isn't that we lack smart people, or powerful rockets, or advanced technology. The challenge is that space operates on scales and speeds that don't accommodate human timelines or convenience. When an object is already moving away from you faster than you can travel, when it has a head start measured in millions of kilometers, when you have no spacecraft prepared and almost no realistic time to act, the physics becomes impossible regardless of how much money you throw at it or how many people work on it. You can't engineer your way around the speed of light. You can't wish away the rocket equation. You can't compress years of spacecraft development into days just because you need to. So where would we even start? If we had to try, if somehow the situation demanded an attempt despite all these overwhelming challenges, what options would we actually have available? That's the question we need to explore next, and I'll warn you now, every option comes with its own set of seemingly insurmountable problems. When most people think about stopping an asteroid or comet, their first instinct jumps straight to nuclear weapons. It makes intuitive sense. Nuclear bombs are the most powerful devices humanity has ever created. They release energy on scales that dwarf anything else in our arsenal. If you want to move something massive, if you want to deliver enough force to change the trajectory of an object several kilometers across traveling at interstellar speeds, it seems logical that you'd reach for the biggest hammer available. So let's seriously examine this option. Could we use a nuclear weapon to stop 3I Atlas? First, we need to understand how nuclear weapons actually work in space, because it's profoundly different from how they work in an atmosphere. On Earth, when a nuclear weapon detonates, the explosion creates an enormous fireball that heats the surrounding air to millions of degrees. That superheated air expands violently, creating a devastating shockwave, a wall of compressed air moving faster than the speed of sound that destroys everything in its path. The shockwave is actually what causes most of the destruction from a nuclear blast on Earth. But here's the critical difference. Space has no air. There's no atmosphere to compress. There's no medium to carry a shockwave. In the vacuum of space, a nuclear detonation looks very different. You still get the release of enormous energy. That part doesn't change. But instead of a shockwave, you get intense thermal radiation, electromagnetic pulses, and a burst of high-energy particles. The energy radiates outward in all directions as light, heat, and radiation, but without air to push against, there's no concussive force. So how would this affect 3I Atlas? The answer depends entirely on how close you could detonate the weapon and what the object is actually made of. Let's imagine the best-case scenario. You somehow manage to deliver a nuclear warhead to 3I Atlas and detonate it on or very near the surface. The thermal energy from the blast would vaporize material from the comet itself. This rapid vaporization would create jets of gas and debris shooting away from the surface, and through basic physics, Newton's third law, action and reaction, those jets would push back against the object, potentially creating thrust that could alter its trajectory. This is actually a legitimate concept that planetary defense researchers have studied. It's called nuclear ablation, and under the right circumstances it could work. But now, we hit the complications. First, 3I Atlas is estimated to be up to around 5 to 6 kilometers in diameter, though it could be smaller. That's enormous. We're not talking about a small boulder or even a mountain-sized rock. We're talking about an object with mass measured in trillions of tons. The amount of momentum carried by something that massive moving at interstellar speeds is almost incomprehensible. To meaningfully change its trajectory, not just nudge it slightly, but actually alter its course enough to stop it, or prevent it from leaving the solar system, you'd need to impart massive amounts of momentum in the opposite direction. One nuclear weapon, even the largest ever built, wouldn't come close. Let's talk about the actual numbers for a moment, though I promise not to drown you in calculations. The largest nuclear weapon ever detonated was the Soviet Tsar bomber, which released energy equivalent to 50 million tons of TNT. Sounds devastating, right? But when you calculate how much momentum that would transfer to an object with the mass of 3I Atlas, considering its current velocity and the inefficiency of energy transfer in space, you're looking at a velocity change measured in centimeters per second at best. Maybe you could alter its course by a fraction of a degree. Over millions of kilometers that might accumulate to something measurable, but it wouldn't stop the object. It wouldn't even slow it down in any meaningful way. It would still be leaving our solar system, just on a very slightly different trajectory. You might think, fine, use multiple nuclear weapons, detonate several in sequence, or arrange them strategically around the object, or keep hitting it until you've changed its course enough. In theory, that could work if you had unlimited time, unlimited weapons, and perfect ability to coordinate. But we have none of those things. Building nuclear weapons isn't like assembling furniture. Each one represents sophisticated engineering, rare materials, complex manufacturing processes, and strict international controls. The idea of rapidly deploying dozens of them to intercept an interstellar object isn't realistic, and that brings us to an even more fundamental problem: delivery. How do you get a nuclear warhead to 3I Atlas in the first place? Remember, this object is already past us and moving away faster than our spacecraft can travel. You'd need to build a mission specifically designed to catch up to it, match its trajectory at least well enough to get close, deliver the warhead to the precise location, and detonate it at the precise moment for maximum effect. Every part of that sentence represents years of development time under normal circumstances. We're talking about an impossibly short time frame. There is no spacecraft sitting ready that could perform this mission. The rockets we have, the most powerful ones humanity has ever built, were designed for different purposes. They can send payloads to Mars, to Jupiter, even to the outer solar system. But those missions take months or years, and they're travelling to destinations that are essentially stationary compared to interstellar objects. Building a rocket capable of the velocity we'd need, designing a spacecraft that could survive the acceleration and then perform the intercept, integrating a nuclear warhead safely into that spacecraft, testing everything to ensure it would actually work. You're looking at years of development time minimum, probably closer to a decade for something this ambitious. Even if we had the spacecraft ready to go, sitting on a launch pad fueled and waiting, we'd face navigation challenges that go beyond anything we've attempted. Hitting a moving target in space requires extraordinary precision. When NASA's DART spacecraft intercepted the asteroid Dimorphos, it was the result of years of trajectory planning, course corrections during flight, and sophisticated autonomous navigation systems that guided the final approach. And that was with detailed knowledge of the target's position, size, and motion. With 3i Atlas, we'd be attempting something far more difficult, with far less preparation and far less margin for error. Then there's the question of targeting. Where exactly would you detonate the weapon for maximum effect? If you're trying to use nuclear ablation, vaporizing material to create thrust, you need to know what the object is made of. Is 3i Atlas mostly ice, which would vaporize easily? Is it rock, which would require much more energy? Is it some combination we're not familiar with? Is its structure uniform, or does it have dense cores and lighter outer layers? We have general observations, but nothing like the detailed composition data you'd want for mission planning. Detonate in the wrong place or at the wrong distance, and you might shatter the object into fragments instead of deflecting it. Congratulations, instead of one interstellar visitor, now you have hundreds of smaller pieces, all still leaving the solar system but now much harder to track or intercept. There's also the political and legal reality. Nuclear weapons in space are governed by international treaties. The Outer Space Treaty of 1967 prohibits placing nuclear weapons in orbit or on celestial bodies. While a mission to intercept 3i Atlas might technically not violate the letter of that treaty, depending on how it's executed, you'd still need international cooperation and approval. In an emergency threatening Earth, nations might set aside diplomatic concerns, but for a hypothetical mission to stop an object that poses no threat, the political coordination alone could take longer than the window of opportunity we have. Let's be honest about what the nuclear option represents. It's our instinct to reach for the biggest tool when facing a massive problem. And in some scenarios, with enough advance warning, with detailed preparation, with proper spacecraft design and international coordination, nuclear deflection could be part of a planetary defense strategy. Researchers genuinely study this approach because for certain types of threats, it might be the only option powerful enough to work. But for 3i Atlas, right now, with the constraints we're facing, it's not that nuclear weapons wouldn't theoretically help. It's that we have no way to deliver them in time, no spacecraft capable of the intercept, no ability to coordinate the mission in the extremely limited time available, and even if we could somehow solve all those problems, the effect wouldn't be enough to stop an object this size moving this fast. The nuclear option fails not because the concept is wrong, but because everything needed to execute it doesn't exist and couldn't be created fast enough. So let's move on to the next possibility, one that doesn't require nuclear weapons but relies instead on something we've actually proven works. If nuclear weapons seem too complicated, too politically fraught, too uncertain in their effects, what about something simpler? What about just hitting the object with a spacecraft? This isn't science fiction. We've actually done this. NASA's DART mission successfully crashed a spacecraft into the asteroid Dimorphos in September of 2022 and measurably changed its orbit. It was a historic achievement, the first time humanity deliberately altered the motion of a celestial object. If we can do it once, why couldn't we do it again with 3i Atlas? The concept behind a kinetic impactor is beautifully straightforward. You accelerate a spacecraft to the highest speed you can achieve, aim it precisely at your target, and ram into it at tremendous velocity. The spacecraft transfers its momentum to the target, and basic physics does the rest. It's like hitting a pool ball with a cue ball, except you're playing on a table the size of the solar system, and the balls are moving at thousands of kilometers per second. But the principle holds, momentum is conserved, and if you hit something hard enough, you change its trajectory. DART proved this concept works. The spacecraft, about the size of a golf cart, slammed into Dimorphos at over 20,000 kilometers per hour. The impact changed the asteroid's orbital period by 33 minutes, more than the mission planners had predicted. It was such a clean success that it validated years of theoretical work and established kinetic impact as a viable planetary defense technique. So if it worked for Dimorphos, why wouldn't it work for 3I Atlas? Let's examine the differences, because they're everything. Dimorphos is a relatively small asteroid, measuring about 160 meters across. 3I Atlas is estimated at up to around 5 or 6 kilometers across, potentially 30 or more times larger in diameter. But size scales matter tremendously when you're talking about mass and momentum. Volume increases with the cube of diameter, which means 3I. Atlas isn't just bigger. It's orders of magnitude more massive. We're comparing something like a large building to something the size of a city. The amount of momentum you'd need to transfer to noticeably affect 3I Atlas's trajectory is exponentially larger than what DART delivered. More importantly, Dimorphos was in a stable orbit around a larger asteroid called Didymos, both of which orbit the Sun in predictable paths within our solar system. The DART team had years to study the system, calculate precisely where Dimorphos would be, and plan an intercept trajectory that would deliver their spacecraft to exactly the right place at exactly the right time. They launched DART in November of 2021, and it reached its target 10 months later. 10 months of flight time. 10 months during which the target remained exactly where the calculations predicted it would be. 10 months to make course corrections and fine-tune the approach. 3I Atlas is nothing like that comfortable scenario. It's not in a predictable solar orbit. It's on an escape trajectory, moving away from us, accelerating as it falls outward from the Sun's gravitational well. Every day it travels farther. Every hour makes the intercept harder. You don't have 10 months. You don't have 10 weeks. You have very little time before the window becomes so difficult that even theoretical interception becomes impossible, and weeks at most before the object is so far away that no realistic mission could ever catch up. And then there's the speed problem. DART worked because the spacecraft could reach the necessary velocity using existing rocket technology combined with a gravity assist from Earth. The entire mission was designed around trajectories that were challenging but achievable with current propulsion systems. Catching 3. Atlas would require speeds we've never achieved with a spacecraft large enough to deliver meaningful impact energy. Remember, this object is moving at interstellar velocities, speeds that allow it to escape the Sun's gravity entirely. Matching that speed, let alone exceeding it to catch up, would require propulsion capabilities beyond what any existing spacecraft possesses. Let's think about what catch-up actually means in practical terms. Imagine 3I Atlas is already millions of kilometers away and pulling farther ahead every moment. To intercept it, you'd need to launch on a trajectory that not only aims for where it is now, but where it will be when you arrive, accounting for the fact that it's constantly moving farther away. You'd need to build up enough speed to not only match its velocity, but exceed it, close the distance, and still have enough relative velocity that the impact delivers meaningful momentum transfer. The faster you're going relative to the targeted impact, the more momentum you transfer, but the harder the navigation becomes, and the more precisely you need to aim. Even if we could somehow build and launch such a mission, immediately the energy requirements present another barrier. DART was relatively small and light because it didn't need to be large to accomplish its goal with Dimorphos. To affect 3I Atlas, you'd need a much more massive impactor or a much higher velocity or both. More mass means heavier spacecraft, which means more powerful rockets, which means more complexity and more time to prepare. Higher velocity means more advanced propulsion, possibly nuclear engines or ion drives running for extended periods, which again brings us back to technology that exists in research labs but not in flight-ready spacecraft sitting on launch pads. There's also the question of whether a single impact would even work. With Dimorphos, one solid hit was enough to measurably change its orbit because the asteroid is relatively small and was already in a stable system where small changes accumulate over time. 3I Atlas is leaving the solar system. To meaningfully affect its trajectory, to stop it or prevent it from escaping, you'd need to change its velocity by a substantial amount. One impact, even a massive one, probably wouldn't cut it. You'd need multiple spacecraft, multiple impacts, coordinated to hit from angles that maximize the cumulative effect. Each impact would cost billions and take months or years to prepare and execute, even under the best circumstances. Here's the sobering reality. The kinetic impactor approach is legitimate planetary defense technology. It works. DART proved that beyond any doubt. But it works for asteroids in our solar system that we can study for years, plan for carefully, and reach with existing technology when we have the luxury of time. It's designed for the scenario where we detect a potentially hazardous asteroid decades before it might hit Earth, giving us time to launch a mission, make course corrections, and deliver the impact precisely when and where we need it. It's not designed for emergency response to an object already leaving our neighborhood faster than we can chase. If we'd detected 3I Atlas years earlier, before it entered the inner solar system, a kinetic impactor approach might have been viable. Launch a mission to meet it on its way in, impact it before it reached perihelion, change its trajectory while we had the advantage of time and better relative velocities. But we didn't have that warning, and we don't have that luxury. The object is already past us and leaving, and the window for kinetic impact has effectively closed or is closing so rapidly that mounting a mission in time is beyond current capabilities. The lesson here isn't that kinetic impactors don't work. The lesson is that timing matters more than almost anything else in space. The right tool at the wrong time becomes the wrong tool. DART succeeded because everything aligned. The technology, the target, the timeline, the preparation. With 3I Atlas, none of those elements align. So what else could we try? There's one more option, worth exploring, one that's more elegant and requires less brute force, but comes with its own devastating limitation. Sometimes the most sophisticated solution doesn't involve hitting something, or exploding something, or throwing raw energy at a problem. Sometimes the elegant approach wins. This brings us to what many planetary defense researchers consider the ideal long-term deflection method, the gravity tractor. If you haven't heard of this concept, prepare to appreciate how clever physics can be when you give it enough time to work. Here's how a gravity tractor operates. You send a spacecraft to rendezvous with the asteroid or comet you want to deflect. Instead of crashing into it or detonating anything near it, your spacecraft simply hovers nearby, maybe a few hundred meters away, using its thrusters to maintain a fixed position relative to the object. Now, here's the beautiful part. Your spacecraft has mass, and anything with mass generates gravitational attraction. It's tiny compared to planetary or stellar gravity, but it exists. The spacecraft and the asteroid attract each other gravitationally. The spacecraft uses its thrusters to hold position, but there's nothing holding the asteroid in place. Over time, the gravitational attraction between them gradually pulls the asteroid toward the spacecraft, very slightly, changing its trajectory. The changes per day are microscopic. We're talking about velocity changes measured in fractions of millimeters per second. But space is patient, and if you have years or decades, those microscopic changes accumulate into significant trajectory alterations. Think about it like this. If an asteroid is heading toward Earth and will arrive in 20 years, deflecting its path by even a few meters per day adds up over that time span. By the time it reaches where Earth would have been, it misses by thousands or millions of kilometers. You don't need to dramatically change the object's velocity. You just need to change it slightly, early enough that the difference compounds over the remaining distance. The advantages of this approach are numerous and compelling. First, it's incredibly precise. Because you're applying constant gentle force rather than a single violent impact, you can adjust the deflection in real time. If you need to alter the trajectory more in one direction, you position the spacecraft accordingly. If you need to fine-tune the approach, you make small adjustments to your thrusting. Second, you don't need to know the exact composition or structure of the target object. You're not depending on how it reacts to impact or explosion. You're just using gravity, which works the same regardless of whether you're dealing with ice, rock, or metal. Third, you don't risk fragmenting the object. A nuclear blast or kinetic impact could potentially break an asteroid into pieces, turning one problem into many. Gravity traction keeps everything intact. For all these reasons, planetary defense researchers love the gravity tractor concept. It's clean, controllable, and reliable given enough time. If we detected an asteroid decades before potential impact, this would likely be the preferred method. No explosions, no high-risk impacts, just patient application of physics until the danger passes by Earth harmlessly. It represents the kind of mature, thoughtful approach to space hazards that a truly advanced civilization would use. So why wouldn't it work for 3i Atlas? The answer, I'm sure you've already guessed, comes down to one brutal constraint: time. Or more precisely, the complete absence of time. Remember those microscopic changes accumulating over years or decades? That's not a figure of speech. For a gravity tractor to work, you genuinely need years at minimum, often decades, sometimes even longer, depending on the mass of the object and how much deflection you need. Let's put numbers to this to make it concrete. A spacecraft with reasonable mass hovering near 3i Atlas would exert gravitational force that might change the comet's velocity by a few millimeters per second per year, not per day, per year. And that's being optimistic. The actual calculations depend on the spacecraft's mass, the distance it can safely maintain, and 3i Atlas's composition and mass. But the order of magnitude is clear. You're looking at effects that take enormous time spans to become meaningful. To stop 3i Atlas, to actually prevent it from leaving the solar system, you'd need to change its velocity by kilometers per second. It's moving at speeds that allow it to escape the sun's gravitational pull. Reducing that velocity to the point where it would no longer escape would require altering its speed by significant amounts. At a few millimeters per second per year, you're looking at timeframes measured in centuries, possibly millennia. Not years, not decades, centuries. You could position a gravity tractor near 3i Atlas and leave it running continuously, and your distant descendants might see the beginning of meaningful results. And that's assuming you could position the spacecraft in the first place, which brings us back to all the same problems we faced with the kinetic impactor. The object is already moving away. You'd need to launch a mission, catch up to it, match its trajectory well enough to maintain a fixed position nearby, and then hold that position for timescales that dwarf human lifetimes. The propulsion requirements for maintaining station keeping near an object moving at interstellar speeds, continuously thrusting to counteract the gravitational pull and maintain your position, would be immense. You'd need power systems that could operate reliably for decades or centuries, fuel supplies or energy generation that wouldn't run out, systems robust enough to handle the radiation environment of deep space for extended periods. Even if we had decades instead of days, even if 3i Atlas were detected years earlier on its way into the solar system, the gravity tractor approach would still face challenges. The object's high velocity and escape trajectory mean you'd need much more deflection than typical asteroid scenarios. For an asteroid in a regular solar orbit, you're often just trying to alter its path slightly so it misses Earth. For an interstellar visitor, you'd be trying to fundamentally change its trajectory from escape to capture, or at least from escape to something that remains in the solar system longer. That's a much bigger ask. The physics doesn't lie. Gravity traction is a brilliant technique for the right scenario, but this isn't that scenario. This is almost perfectly the wrong scenario. An object moving too fast, already past us, on an escape trajectory with essentially no warning time. If you were designing a situation where a gravity tractor absolutely couldn't work, you'd be hard-pressed to come up with something more difficult than 3i Atlas presents. There's something almost poetic about this failure, though. The most elegant solution, the one that uses the fundamental force of gravity itself to gently guide objects away from danger, requires the one thing we can't manufacture or accelerate: time. You can build bigger rockets, you can develop more powerful weapons, you can improve sensors and computers and navigation. But you can't create more time. Once it's gone forever, and with every hour that passes, 3i Atlas travels farther into a future where no amount of technology can bring it back within reach. So we've examined three distinct approaches: nuclear deflection, kinetic impact, and gravity traction. Each has merit in the right circumstances. Each represents legitimate science that researchers actively study for planetary defense purposes. And each fails completely for 3i Atlas because of one overwhelming factor that transcends technology and physics and engineering. We need to confront what that factor really means, and whether there's any scenario where we could have succeeded. Everything we've explored so far leads to one inescapable conclusion. The biggest barrier isn't our technology or our knowledge or our capabilities, it's time, specifically the absence of it. So let's run a thought experiment. What if we'd seen 3i Atlas coming years earlier? What if our detection systems had spotted it while it was still far from the sun, giving us years instead of days to plan and execute a response? Would that change everything? The answer is complicated but hopeful. More time wouldn't magically solve all the problems. Physics remains physics, and interstellar speeds remain interstellar speeds. But it would transform many impossible challenges into merely extremely difficult ones. Let's walk through what advance warning would actually give us, and whether it would be enough. First, consider the detection challenge itself. Interstellar objects are incredibly difficult to spot. They're typically dark, reflecting very little sunlight. They're moving on trajectories that don't match the predictable orbits of solar system objects, so they don't appear where survey telescopes expect to find asteroids. They're often discovered only after they've already entered the inner solar system and brightened enough to stand out against background stars. Humanity only confirmed the existence of interstellar visitors starting in 2017 with the discovery of Oumuamua. Before that, we'd theorized such objects existed, but we'd never definitively detected one. Our detection capabilities are improving rapidly. New survey telescopes with wider fields of view and more sensitive cameras are coming online. The Vera Rubin Observatory, set to begin operations soon, will scan the entire visible sky every few nights, cataloguing everything that moves or changes. Systems like this dramatically increase our chances of detecting interstellar visitors earlier in their journey through our solar system. But even with perfect detection systems, there's a fundamental limit. These objects are faint until they get relatively close. Spotting one while it's still years away from perihelion would require capabilities we're still developing. Let's imagine we somehow managed it though. Let's say we detected 3I Atlas, a decade before it reached the Sun, giving us 10 years of warning. What would become possible? Start with the simplest benefit: time to plan. Instead of panicking about what to do with days to decide, we'd have years to study the object, calculate its trajectory precisely, model different intervention scenarios, and choose the optimal approach. We could send exploratory probes first to gather data about its composition, structure, rotation, and surface features. That information would be invaluable for planning any deflection attempt. For the nuclear option, 10 years would allow us to design and build a specialized mission. We wouldn't be trying to retrofit existing spacecraft or rush untested designs into production. We could engineer a vehicle specifically for this purpose, with propulsion systems optimized for the intercept, navigation capable of the precision needed, and payload integration done properly with full testing. We could model the ablation effects on different types of comet material, run simulations, and design the warhead placement for maximum efficiency. We could even launch multiple spacecraft with different warheads, creating redundancy in case one mission failed. The catch-up problem would still exist. 3I Atlas would still be moving at interstellar speeds, but intercepting it before perihelion would offer significant advantages. Objects on hyperbolic trajectories slow down as they approach the Sun due to the star's gravity, even though they maintain enough velocity to eventually escape. The closer you can intercept before perihelion, the lower the relative velocity you need to match. That makes the propulsion requirements more manageable, and the navigation more forgiving. It's still extraordinarily challenging, but it transitions from impossible to merely at the edge of current capability. For a kinetic impactor approach, advance warning becomes crucial. The DART mission took about 5 years from serious planning to impact. Concept development, detailed design, construction, testing, launch, and flight time. With a decade of warning, we could follow a similar timeline without cutting corners. More importantly, we could time the impact for maximum effect. Instead of trying to catch an object that's already leaving, we could arrange to meet it on its way in, when relative velocities are more favorable, and when any deflection we achieve has time to compound as the object continues its trajectory. Think about it this way. If you deflect an object's path slightly when it's still far from the Sun, that small change grows larger the farther it travels. By the time it reaches where it would have perihelioned, the difference could be substantial. You might not stop it entirely. Remember, we're dealing with an escape trajectory, but you could potentially alter its path enough to affect where it goes after leaving our solar system. With years of lead time and multiple impacts timed carefully, you might accumulate enough trajectory change to matter. The gravity tractor option benefits most from advance warning because it needs time more than any other method. Position your spacecraft years before perihelion. Maintain your gravitational pull throughout the object's passage through the inner solar system, and the accumulated deflection could actually reach meaningful levels. We're still talking about small changes. This method remains gentle and gradual. but years of constant pull could bend the trajectory noticeably. Combine this with careful positioning to maximize the effect during the periods when the object moves slowest, and you have a scenario where gravity traction transitions from hopeless to potentially viable. But even with perfect advance notice, we need to be honest about the fundamental challenge. 3I Atlas is on a hyperbolic trajectory with substantial velocity excess. That means it has more than enough energy to escape the solar system. To truly stop it, to capture it into a bound orbit around the Sun, would require removing a massive amount of kinetic energy. We're not talking about nudging it slightly. We're talking about fundamentally changing its relationship with the Sun from passing through to gravitationally captured. The energy requirements for that are staggering even with years of warning. A more realistic goal with advance notice would be altering its trajectory rather than stopping it completely. Change where it goes after leaving the solar system. Modify its path through the inner solar system to bring it closer to Earth for better observation, or farther away if there were any concern about hazards. These more modest goals become achievable with sufficient warning and proper mission planning. You're working with the object's trajectory rather than fighting against it entirely. The real lesson from this thought experiment is that early detection matters more than almost any other factor in planetary defense. The difference between detecting a threat decades in advance versus detecting it when it's already upon you is the difference between having options and having none. It's the difference between carefully planned response and desperate improvisation. It's the difference between using sophisticated techniques like gravity tractors and falling back on brute force approaches that may not work at all. This is why so much effort in planetary defense focuses on detection and tracking. The Planetary Defense Coordination Office at NASA doesn't spend most of its time designing deflection missions. It spends time improving our ability to find potentially hazardous objects earlier. Every year we push back the detection boundary, every improvement in telescope sensitivity, every new survey system that comes online. These advances don't just give us better data. They give us something far more valuable. Time to respond if we ever need to. For 3I Atlas specifically, even with perfect detection years in advance, we'd still face an extraordinary challenge. This isn't a typical near-Earth asteroid. This is a visitor from beyond, moving on a trajectory that doesn't play by solar system rules, large enough that moving it significantly would require coordinated efforts beyond anything we've attempted. But it would shift from completely impossible to theoretically possible, and that distinction matters. It's the difference between having zero options and having difficult options, between helplessness and agency. Here's what we can take from this. The time factor doesn't just matter for 3I Atlas. It matters for every potential space hazard we might face. The earlier we see something coming, the more options we have, the better we can plan, the higher our chances of success if intervention becomes necessary. This understanding is driving the next generation of space surveillance systems and planetary defense planning. We're building capability not for today's challenges but for tomorrow's, accepting that the best time to solve a space problem is years or decades before it becomes critical. And that brings us to the crucial question. Given everything we've learned about our limitations with 3I Atlas, what does this reveal about where humanity actually stands? We've run through every realistic option for stopping 3I Atlas and found each one wanting. The nuclear approach fails on delivery timelines. The kinetic impactor fails on catch-up physics. The gravity tractor fails on the sheer amount of time required. Even with advance warning, the challenge remains at the very edge of possibility or beyond it. So what does this mean? Does it mean we're helpless? Does it mean all our space? Achievements count for nothing when facing a real challenge? Not at all. What it reveals is something more nuanced and ultimately more important. A clear picture of what we can do, what we can't do yet, and what we need to focus on building. Let's start with what we absolutely can do, because the list is impressive. We can detect objects millions of kilometers away moving against the background of stars. We have telescopes sensitive enough to spot asteroids no larger than a house, at distances farther than the Moon. We have computational capability to calculate trajectories with extraordinary precision, predicting where an object will be years into the future, accounting for gravitational influences from every planet and major body in the solar system. We've sent spacecraft to every planet. We've landed rovers on Mars that have operated for years beyond their design lifetimes. We've sent probes beyond Pluto into interstellar space itself. We've deliberately crashed a spacecraft into an asteroid and measured the exact change in its orbit. That last achievement deserves emphasis because it's recent and directly relevant. The DART mission in September of 2022 wasn't just a technical demonstration. It was proof that humanity can intentionally alter the cosmos. We identified a target, built a spacecraft, launched it into space, navigated across millions of kilometers, and impacted exactly where we intended with enough force to measurably change the target's motion. For the first time in human history, we proved we're not entirely at the mercy of celestial mechanics. We can push back, we can change outcomes. That's profound. We also have nuclear weapons, like them or not, and we understand the physics of how they could be used for planetary defense. We have international cooperation frameworks. Space agencies from different nations collaborate regularly on missions and data sharing. We have the scientific knowledge to model asteroid deflection, to calculate energy requirements, to understand orbital mechanics at levels that would seem like magic to people just a few generations ago. We have rocket engines that can lift enormous masses into orbit and send them on trajectories throughout the solar system. All of this is real capability that exists right now. But we also need to be honest about the gaps. We have no emergency response spacecraft sitting ready for rapid deployment to unexpected threats. Everything we launch takes years from concept to completion, and that's for missions to predictable targets we've had time to study. We don't have propulsion systems that can achieve interstellar speeds or anything close to them. Our fastest probes move at velocities that would take tens of thousands of years to reach even the nearest stars. We haven't built spacecraft with power systems that can operate reliably for the decades or centuries that techniques like gravity tractors require. We don't have international protocols established for rapid decision-making about planetary defense measures that might involve nuclear weapons. Perhaps most importantly, we don't have the infrastructure to respond to very short-notice threats. Our entire space program is built around careful planning, extensive testing, and methodical execution. Those aren't flaws, they're features that keep missions successful and astronauts safe. But they mean we can't pivot quickly when surprise situations arise. We're like a chess player who's excellent at strategy and execution given time to think, but struggles with speed chess, where decisions must be made in seconds. What about interstellar objects specifically? Here the capability gap becomes stark. 3. I-Atlas is only the third confirmed interstellar visitor we've detected. The first, Oumuamua, appeared in 2017. The second, Comet Borisov, came through in 2019. 3 objects total. We barely understand these visitors. Each one has surprised us with its properties and behavior. We don't have a comprehensive catalogue of interstellar object types. We don't have detailed composition data. We don't have experience intercepting them or interacting with them in any controlled way. They represent a category of space object we're only beginning to understand. The speed differential is perhaps the clearest limitation. Everything in our solar system is gravitationally bound to the Sun and moves at velocities that, while fast by human standards, are manageable for spacecraft design. Interstellar objects are playing by different rules. They're not bound to our star. They're moving through our neighborhood on their way to somewhere else. Matching those velocities with current propulsion technology is extraordinarily difficult, possibly impossible for larger missions that would carry enough mass to meaningfully interact with the object. But here's what gives me optimism. We're improving faster now than at any point in history. Detection systems are getting dramatically better. The difference between what we could see a decade ago and what we can see now is remarkable, and the next decade will bring even more improvement. DART-proved deflection works, and follow-up missions are already being planned to refine the technique. International cooperation on planetary defense is strengthening. Nations are conducting coordination exercises, sharing data, and recognizing this as a shared challenge that transcends borders. Propulsion technology is advancing. Ion drives, nuclear engines, and other advanced concepts are moving from theory to practical development. Power systems for deep space missions are improving. Our ability to operate spacecraft for extended periods in harsh environments grows with every mission. We're learning from every probe we send, every asteroid we study, every challenge we overcome. The gap between what we can do and what we'd need to do to address something like 3I Atlas is narrowing. Think about the trajectory of human capability. In space, we went from first satellite to moon landing in 12 years, from first spaceflight to space stations in 2 decades. from no knowledge of asteroids beyond Earth's orbit to detailed mapping of thousands of near-Earth objects in a generation. The pace of advancement is extraordinary when you step back and look at the arc. What seems impossible today becomes routine tomorrow. What requires years of planning today will eventually be accomplished in months or weeks as technology improves and experience accumulates. The lesson from 3i Atlas isn't that we're incapable. The lesson is that we know exactly where we stand. We can handle threats in our immediate neighbourhood given sufficient warning. We can detect and track objects throughout the solar system. We can intervene in asteroid trajectories when we have time to plan and execute. What we can't do yet is respond to sudden threats from interstellar space with days of notice. That's not a failing. It's a milestone marking where we are on the journey toward becoming a truly spacefaring civilization. Every limitation we identify becomes a target for improvement. Every capability gap becomes an engineering challenge to solve. This is how progress happens. Honest assessment of what works, what doesn't, and what needs to be built next. And that honest assessment leads us to an equally important question. We've spent considerable time exploring whether we could stop 3i Atlas, working through the physics and technology and limitations. But step back for a moment and consider a different question entirely. Should we? Even if we had the capability, even if we could wave a magic wand and suddenly possess the technology to intercept and deflect this interstellar visitor, would it be the right thing to do? This might seem like an academic question. After all, we've established we can't do it anyway, so why debate whether we should? But the ethical framework matters because it shapes how we think about planetary defense, how we prioritize resources, and how we respond to different types of objects in the future. Not every object we detect requires intervention, and learning to distinguish between genuine threats and valuable opportunities is part of maturing as a spacefaring civilization. Let's start with the scientific perspective. Interstellar objects are extraordinarily rare and valuable. 3i Atlas is only the third such object we've confirmed in all of human history. Think about what that means. We've been observing the sky for thousands of years with varying degrees of sophistication, and we've confirmed exactly 3 visitors from beyond our solar system. Each one is a treasure trove of information about the galaxy beyond our neighbourhood. Each one carries data about stellar system formation, about the composition of material around other stars, about the conditions in interstellar space, about the physics of objects that can survive millions of years travelling between stars, when Oumuamua passed through. In 2017, scientists were desperate to learn everything possible. Its unusual shape, its slight acceleration that wasn't entirely explained by normal outgassing, its trajectory and composition, every detail sparked questions and debates that continue today. We didn't have enough data. We couldn't study it closely enough. It was gone before we fully appreciated what we were looking at. With Comet Borisov in 2019, we were better prepared. We observed it extensively, measured its composition, studied how it compared to solar system comets. The findings were fascinating. In many ways, it resembled comets from our own neighbourhood, but with subtle differences that hinted at different formation conditions. Now imagine we had the capability to stop or deflect 3i Atlas. In doing so, we'd potentially destroy or fragment an object that might never be replaced in our lifetimes. We'd eliminate the chance to study it up close, to send probes that could land on its surface and analyse material that formed around a different star. We'd be choosing intervention over observation, action over learning. Unless the object posed a genuine threat, that would be scientific vandalism of the highest order. And here's the key point. 3i Atlas doesn't threaten us. Its trajectory is clear. It came into the solar system, past the Sun, and is leaving. At no point does it come close to Earth. There's no collision risk, no danger of impact, no hazard to satellites or spacecraft. It's simply passing through, a visitor from elsewhere that happens to be travelling through our cosmic neighbourhood on its way to somewhere else. In what universe does it make sense to expend enormous resources and potentially destroy a scientifically priceless object that poses zero threat? This brings us to the broader question of resource allocation. Planetary defense isn't free. Building detection systems costs billions. Developing deflection technology requires sustained funding and expertise. Maintaining readiness for potential threats demands ongoing investment. We have to make choices about where that money and effort goes. Should we focus on detecting and preparing to deflect near-Earth asteroids that could actually hit us? Or should we spend resources developing capability to intercept harmless interstellar visitors, The answer seems obvious when framed that way, but it's worth stating explicitly. There are thousands of near-Earth asteroids we haven't discovered yet, some of which could pose genuine threats to Earth. We know statistically they exist. We know eventually one will be on a collision course, whether that's next decade or next century or next millennium. The more of them we find, the better we can assess the actual risk landscape and plan for mitigation if necessary. Every dollar spent on detecting real threats is a dollar invested in actual safety. Compare that to spending billions developing capability to intercept interstellar objects that pose no danger. The objects are scientifically valuable, not threatening. They're rare enough that even if we built the capability, we might wait decades or longer for another one to appear, and when it does, the odds are overwhelming that it won't be on a threatening trajectory either. The interstellar space is vast. The odds of a random object from outside our solar system happening to be aimed precisely at Earth are infinitesimally small. It's far more likely they pass through harmlessly, just like 3I Atlas. There's also international law to consider. The Outer Space Treaty, ratified by over 100 countries, establishes space as a global commons. Activities in space are supposed to benefit all humankind, and nations are supposed to coordinate on actions that might affect the space environment. While the treaty doesn't explicitly address deflecting interstellar objects, the spirit is clear. Space isn't a place for unilateral action without international consensus, especially when nuclear weapons or other powerful interventions might be involved. If 3I Atlas were on a collision course with Earth, international consensus would form quickly. Self-defense is universally recognized, but deflecting an object that poses no threat. That would require a level of international agreement that would take years to achieve, involving not just space agencies but diplomatic channels, legal frameworks and ethical review, and rightfully so. The precedent of intervening in celestial mechanics without clear justification could lead to all sorts of problematic scenarios in the future. Here's the mature perspective. Being capable of something doesn't mean we should do it. Wisdom involves knowing when to act and when to observe. A truly advanced civilization doesn't flex its muscles unnecessarily. It doesn't interfere when interference adds no value and potentially destroys something valuable. It prioritizes real threats over hypothetical ones, directs resources toward actual safety rather than demonstrations of capability, and recognizes that sometimes the right choice is to watch and learn rather than to intervene. This distinction between objects that threaten us and objects that simply interest us is crucial for planetary defense planning. We need robust capability to detect and deflect actual threats. We need international cooperation frameworks for decision-making when genuine danger appears. We need continued investment in detection systems, deflection technology, and early warning infrastructure. All of that is justified and important. But we also need wisdom to recognize when an object is a gift of scientific opportunity rather than a threat, and the restraint to treat it accordingly. 3I Atlas is that gift. It's a visitor from beyond, carrying information about regions of space we may never reach in person, composed of material that formed in conditions we can only study from afar. The right response isn't to stop it. The right response is to observe it, learn from it, gather as much data as possible, and hope that more such visitors come through in the future. Each one teaches us something new about the galaxy we inhabit. Each one expands our understanding of what's possible, what's common, what's rare in the cosmos. That knowledge is worth far more than any demonstration of deflection capability against a harmless target. So with all of this context, the technical limitations, the ethical considerations, the priorities that matter, what's the actual answer to our original question? So here we are at the end of our investigation, and it's time to answer directly. Could we stop 3I Atlas? The honest, straightforward answer is no, not with current technology, not with the time frame available, not with anything close to the resources we'd need and the capabilities we'd have to possess. It's not that the laws of physics prohibit it in principle. It's that the practical barriers are too numerous and too severe to overcome. But that answer is just the beginning of what we've actually learned here. Let's be specific about why we couldn't do it. 3I Atlas is already moving away from us at interstellar speeds, velocities high enough to escape the sun's gravitational influence entirely. That means any spacecraft we launched would need to not only match that speed but exceed it significantly to catch up before the object gets too far away. We don't have propulsion systems capable of that kind of rapid acceleration to those velocities. Our fastest spacecraft achieved their speeds through years of carefully planned gravity assists and sustained thrust. We don't have years, we have days before the window of opportunity begins to close so tightly that even theoretical missions become impossible. Even if we somehow had a spacecraft ready to launch immediately, fully fueled and prepared, we'd face the navigation challenge of intercepting a target that's millions of kilometers away and moving farther every moment. The precision required would be extraordinary, beyond what we've demonstrated even in our most successful missions. And even if we somehow overcame that hurdle and reached 3i Atlas, what then? The object is several kilometers across, massive beyond easy comprehension, with momentum that would require incredible amounts of energy to alter meaningfully. One nuclear warhead wouldn't be enough. One kinetic impact wouldn't be sufficient. We'd need coordinated efforts involving multiple spacecraft, multiple interventions, sustained application of force over extended periods, none of which we can deliver in the time frame that exists. The time constraint kills every option. Nuclear deflection requires years to design the mission properly, build the spacecraft, integrate the warheads, test everything, and launch. Kinetic impactors need similar timelines plus the flight time to reach the target, and even then they work best against objects much smaller than 3i Atlas. Gravity tractors require decades or centuries to produce meaningful deflection on something this massive moving this fast. Every approach we examined requires the one thing we don't have and can't create, enough time for physics to work at the scales involved. But here's the crucial insight. That's okay. It's okay that we can't stop 3i Atlas because we don't need to. The object poses no threat. Our investigation wasn't about solving an actual emergency. It was about understanding our capabilities honestly. And what we've learned is both humbling and empowering. We're not yet at the level where we can respond to any space scenario with confidence. We have real limitations. Objects moving at interstellar speeds on escape trajectories represent challenges beyond our current technology when timelines are measured in days. We can't snap our fingers and make a mission appear. We can't bend physics to our convenience. We're still bound by the reality of what propulsion systems can achieve, what time frames are needed to build and deploy spacecraft, what energy is required to alter trajectories at these scales. At the same time, we know far more now than we did even a decade ago. We've detected 3 interstellar objects, which means our detection systems are working. We're getting better at spotting these visitors early enough to study them. The DART mission proved we can deliberately alter asteroid trajectories, validating techniques that were purely theoretical before. We have nuclear weapons and understand how they could be applied to planetary defense scenarios. We have international cooperation frameworks, even if they need strengthening. We're building capability steadily, methodically, learning from each mission and each challenge. What would need to exist for us to successfully intercept something like 3i Atlas in the future? Start with detection decades in advance, not days. We need survey systems sensitive enough and comprehensive enough to spot interstellar visitors when they're still far from the Sun, giving us years of warning instead of discovering them when they're already here. That technology is coming. Next-generation telescopes will dramatically improve our detection capabilities over the coming decade. We need dedicated interception spacecraft, not one-off custom missions. Imagine having spacecraft designed specifically for rapid deployment to unexpected targets, perhaps stationed at strategic points in the solar system with propulsion systems pre-tested and ready. Building and maintaining such a fleet would be expensive, but it would transform response times from years to months or weeks. We need better propulsion technology. Nuclear engines that can achieve higher velocities, ion drives that can run continuously for years providing steady acceleration, perhaps even more exotic concepts like fusion drives or antimatter propulsion if we can ever make those practical. Each advancement in propulsion expands the envelope of what's reachable and how quickly we can reach it. We need better modelling of interstellar objects so we understand what we're dealing with when we detect them. Are they mostly ice or rock? How do they respond to impact? What's their structure? Better data means better mission planning and higher success rates. Perhaps most importantly, we need established international protocols for decision-making about planetary defense. Who decides when intervention is necessary? How quickly can consensus form? What legal frameworks govern actions in space that might involve weapons or significant resources? Working these questions out before a crisis arrives is far preferable to trying to improvise during an emergency. The fact that we're having these conversations now, running coordination exercises, sharing data across national boundaries. That's genuine progress. Is any of this happening? Yes. NASA's Planetary Defense Coordination Office exists specifically to address these challenges. Other space agencies worldwide are contributing. Detection systems are improving every year. The DART mission has a follow-up called HERA being prepared by the European Space Agency to study the impact site and learn even more about kinetic deflection. Research into advanced propulsion continues in universities and national labs. International cooperation on space activities grows stronger despite political tensions in other areas. The trajectory is clear. We're building capability, expanding knowledge, preparing for challenges we hope never come but want to be ready for if they do. Here's the perspective that matters. We're the first generation of humans to even ask these questions seriously. Our ancestors looked at comets and asteroids as omens or curiosities, with no conception that they could be understood or influenced. We're the first to detect objects from beyond our solar system. We're the first to deliberately change an asteroid's orbit. We're the first to have even the beginnings of planetary defense capability. That we can't handle every scenario yet doesn't diminish those achievements, it contextualizes them. We're early in this journey, taking the first real steps toward becoming a civilization that's not entirely at the mercy of cosmic chance. 3i Atlas will leave our solar system and continue its journey through the galaxy. It will travel for millions of years through the dark between stars, perhaps eventually entering another stellar system, perhaps wandering the galactic void indefinitely. We'll watch it go with our telescopes, gathering data as long as we can, learning what it can teach us about the universe beyond our immediate neighborhood. And that's the right outcome. Not because we can't stop it, but because we shouldn't want to. It's not a threat, it's a teacher. It showed us where we stand, what we can do, what we need to build, and how far we have yet to go. The real lesson isn't about 3i Atlas, specifically. The lesson is about maturity and wisdom in the face of cosmic challenges. It's about building capability methodically rather than panicking. It's about distinguishing between actual threats that deserve resources and interesting phenomena that deserve study. It's about honest assessment of limitations so we know where to focus improvement efforts. It's about recognizing that becoming a spacefaring civilization is a journey measured in generations, not years, and that each step we take, each capability we build, each mission we complete, moves us closer to being able to handle whatever the universe sends our way. We couldn't stop 3i Atlas, but we learned exactly why, and that knowledge is valuable. Next time an interstellar visitor comes through, and there will be a next time, we'll be better prepared to observe it, study it, and learn from it. Eventually, if we keep building and improving and expanding our capabilities, we'll reach a point where even objects moving at interstellar speeds on escape trajectories become reachable. We'll have the detection systems to see them coming years in advance. We'll have the spacecraft ready to intercept them if necessary. We'll have the international frameworks to decide quickly when action is justified and when observation is wiser. We're not there yet, but we're moving in that direction, and that's what matters. So what do you think? Now that you understand what it would actually take to stop an interstellar visitor, now that you've seen the physics and the limitations and the possibilities, what should humanity prioritize next for planetary defense? Better detection systems to find threats earlier? Faster spacecraft to reach distant objects? International cooperation protocols to coordinate response? Advanced propulsion research to enable missions we can't do today? There's no single right answer, but your perspective matters because this is a shared challenge that affects all of us. Drop your thoughts in the comments. Tell me what you think the next step should be, and if this investigation changed how you think about our capabilities in space, if it gave you a clearer picture of where we stand and where we're heading, hit that like button and subscribe. We'll keep exploring these questions together as our capabilities grow and as new visitors arrive from the vast darkness between stars. Thank you for staying with me through this entire analysis. Now we both know not just what's impossible today, but what might become possible tomorrow.